Hello and welcome to Pre-Calc 30 with Miss Verity. Today we're going to be talking about 1.2 Part 1, Vertical and Horizontal Reflections. A reflection of a graph. So what does this look like? Complete the following table using the coordinates from the given graph. Graph the new coordinates to determine the mirror image with the x-axis as the mirror. What that means is we are going to reflect across the x-axis. So at point A is at -4, -3. If we are reflecting that across the x-axis, that means we're going to reflect it up to the exact distance that it was on the other side. So our new point, this part is not in here, FYI, our new point is -4, +3. Point B is at -2, -3. So to reflect across the x-axis, we're going to go the same distance. So this one's at -3. We're going to go that same distance straight up. So that new point is right there. And that new point is -2, +3. So as I'm going through this, you're looking for patterns. Point C is at 1, 0. If we were to reflect that across the x-axis, well, it's 0 points away from the x-axis. It's going to stay 0 points away from the x-axis. So this point is 1, 0. Point D is at 3, 4. If we were to reflect it, again, we want it the same distance on the other side of the y. So it is 1, 2, 3, 4 units above. If we were to reflect it across the x-axis, it's going to be 1, 2, 3, 4 units below. Its new coordinate is 3, -4. And last but not least, we've got point E. It is at 5, -4. It is 4 units from the x-axis, so if we're going to reflect it across, it's still going to be 4 units across. So we end up at 5, 4. If I was to draw it in, our graph would look like this. Our new graph, that's a reflection across the x-axis. If we're looking at any of our new coordinates compared to our original coordinates, what do you notice? Well, all of our x coordinates stayed the same, but our y coordinates are the negative version. An invariant point is a point on a graph that remains unchanged after transformation is applied to it. It is any point on a curve that lies on the line of reflection. Are there any invariant points? Looking back at our graph, well, the only point that did not change is this point. Fancy name for that point is an x-intercept. Conclusions. When we reflect a graph, y is equal to f of x in the x-axis, the resulting function is y is equal to -f of x. And our mapping notation is x, -y. Exploration number 2. Complete the following table using the coordinates from the given diagram. Graph the new coordinates to determine the mirror image with the y-axis as the mirror. Same graph as last time, except we're going to reflect it across the y-axis. So when we're reflecting it across the x-axis, we always compare to the x-axis. When we're graphing across the y-axis, we're going to compare to the y-axis. Point A is still our -4, -3. It is 1, 2, 3, 4 units from the y-axis. If we're going to reflect it across there, it needs to be the same distance. 1, 2, 3, 4 points. Our new point is 4, -3. Point B is -2, -3. Well, it is 2 units away from the y-axis. It needs to keep that same distance. Our new point is 2, -3. Point C is at 1, 0. If we want to reflect it, it's 1 unit away. It needs to stay 1 unit away. Our new point is -1, 0. Point D is, we're at, what are we at there? 3, 4? So 3 units away from the x-axis, from the y-axis. We need to be 3 units away from the y-axis. And lastly, point E, we are at 5, -4. We are 5 units away from the y-axis. We need to be 5 units away on our y-axis. Our new graph, hopefully with all these new points, I can figure out where we went. There's our new graph. That's a reflection across the y-axis. Our mapping any point, we'll notice from our points how they changed. Our y-coordinates stayed the same, but now it is our x-coordinates that were reflected. Those were the ones that changed. Any invariant points? Points that didn't change, if we want to look back. Points that didn't change was our y-intercept. Conclusions. When we reflect a graph, y is equal to f of x in the y-axis, the resulting function is y is equal to f -x. In our mapping notation, that looks like -x, y. All right, moving on. We've always used set notation to identify each of these. In pre-calculus, we are going to learn interval notation in our description of domain and range. The key points of interval notation is that square brackets means included. So that value means it's part of the set. If we use a round bracket, it's not included. If we want to rewrite these, so set notation, we've got -13 is less than or equal to x, which is less than -5. When we've got an equal to, that means it's included. Our square brackets. And it's all the points in between until -5, which is not included. Negative infinity, well, can we ever actually reach negative infinity? No, we can't, so we're going to use a round bracket. And we're going to 23, which is included. And last but not least, negative infinity to infinity. As I said before, we can never actually reach infinity. So those points are not included. If we're going to go to the reverse way to put our interval into set notation, notice we've got square brackets on both of those, meaning that they are included. So x is less than or equal to 6, which is less than or equal to -3. Our next one, 12 to positive infinity, both of those are included. We've got y, because it's a range, is less than infinity, but is greater than 12. You could also, for that one, write y is greater than 12 and call it a day. And then our last one, a range again, so it's a y. Y is less than or equal to because of the square bracket, 16 greater than -7. Example 1, if f of x is equal to x squared plus 3x plus 1, what would the new equation of the function be if it was reflected in the y-axis? So remember, when we're reflecting in the y-axis, that's our x's becoming our our negative x's. Or we had f of negative x. So just like in chapter 10, where we substituted values, if we have f of negative x, well, that's going to be negative x squared plus 3 times negative x plus 1, which gives us x squared subtract 3x plus 1. If we wanted to reflect it in the x-axis, that means our y's are becoming negative y's. They're the opposite sign of what they were. Or we had negative f of x. So our negative f of x is equal to negative 1 times our x squared plus 3x plus 1. Which if we simplify and distribute our negative 1 to every term, would be negative x squared subtract 3x subtract 1. Example 2, give the coordinates of any point that appears on the graph of f of x is equal to x cubed subtract 5x plus 2. All we're looking for is a coordinate. So pick any point you want, your favorite point. I'm going to pick 1. So 1 cubed subtract 5 times 1 plus 2. That gives us 1 subtract 5 plus 2, which is negative 2. Our point on the graph is 1, negative 2. What would the coordinates be if the function was reflected in the x-axis? So that is where we have our y's changing their sign. We have an x, negative y. This is what our new point would look like. So the new point would be 1, positive 2. If we were to reflect it in the y-axis, we've got our negative x's and our y's staying the same. This point would be negative 1, negative 2. Example 3, graph y is equal to f of x on a graphing calculator, or Desmos, where f of x is equal to x squared plus 4x. Draw a quick sketch of it below. What that looks like is this. This is our f of x. Part B, what would your equation be to graph y is equal to negative f of x, which is a reflection in the x-axis, and then again, y is equal to f of negative x, which is a reflection in the y-axis. So to start off, let's do a reflection in the x-axis. So you've got our negative f of x. What that would look like would be negative x squared plus 4x, which would be negative x squared subtract 4x. To graph that, this point is at negative 4. A reflection across the x-axis would put it at positive 4. I'm going to grab a different color. Our x-intercepts don't change because 0 reflected would still be 0. This point right here is at positive 5. It will go to negative 5. And same with the one on the other side. There is our reflection across the x-axis. To reflect our original across the y-axis, that means our x-coordinates are changing. This point right here is 2, or is at negative 2. It'll end up at positive 2. This point right here is at negative 4. It will end up at positive 4. Our y-intercept was our invariant point. This point right here is at positive 1. It'll end up at negative 1. And its reflecting point is at 1, 2, 3, 4, negative 5. It's going to end up at positive 5. The reflection across the y-axis for our original graph looks like this.